Section 9.3, Logarithmic Functions. In this section we introduce the definition of what a logarithm is, and we show how it's related to the exponential functions. Exponential functions were fairly easy to work with, and once you understand how logarithms and inverses are connected, it's fairly easy to evaluate logarithms and then to talk about some of the properties that logarithms have. This section deals with the definitions and maybe graphing some of the logarithms. In the next section we'll talk about some of the special properties that logarithms have. Having established those, we'll then be ready to talk about solving equations. 9.3 Logarithmic Functions. Let's begin by talking about definitions and notation. We define the logarithmic function in the following way. The logarithmic function with base a as the inverse of the exponential function f of x is equal to a to the x. It's the function that undoes the exponential. So here's our notation. Y is equal to the log base a of x. Okay? Now we read this as, if I'm going to read it in English, and you heard me say it, but I want to write it down in your notes so you have it. This is read as log base a of x. Okay? Now that definition doesn't really clarify too much how we evaluate logarithms, but it is very important that we understand that they do cancel each other out. They are inverses of each other. What's better in terms of understanding the logarithm for computation, that is to actually evaluate logarithms, is the following. It turns out that y equals log base a of x means the same thing as x is equal to a to the y. These are equivalent statements of the relationship of the three variables. Okay? So the x in both cases is just some real number. Okay? The a in both cases has the name of being the base, right? We talked about the base of an exponential. Now we're talking about the base of a logarithm. And then the y, which on this right-hand side is the exponent. On the left-hand side, it's the value of the logarithm. So the value of the logarithm, the output of the logarithmic function, is an exponent. Okay. Now let me show you how you can best see this. Okay. Let's look at a few examples below. According to this statement right here, we can rewrite log base 10 of 100 equals 2 in the following way. Notice how the base is the base of the exponent, right, 10. The value of the logarithm, the output, is the exponent, and then the inside is what it's equal to. Now look at that statement. That's obviously true, right? We know that 100 is 10 squared. Okay? Now here's how you see this, and this is how I picture this. Every time I see a logarithm in my head, here's what I'm looking at. 10 raised to the other side is equal to what's inside the log. Okay? This little spiral picture is how you remember what a logarithm means. So, for example, if you're asked to rewrite logarithms into exponential form, we can do that just remembering this little spiral doohickey, right? That's probably not a formal mathematical term for this, but if I use the phrase spiral doohickey in this lecture, you know what I'm talking about. So 5 raised to the 2 is equal to x. 5 raised to the 2 is equal to x. In other words, x is 25. So we were able to identify what that missing value is by rewriting this as an exponential. If I took b raised to the other side equals to what's inside, I have b to the third is equal to 64, right? Which means b is some number. What? What raised to the third power is 64? I think b would be 4, right? 4 cubed. Yep, is 64. Of course, things could get a little bit hairier, right? 3 raised to the other side equals to what's inside. It'd be 3 to the y is equal to 7. That's a little bit harder, and we're not going to be able to answer that question just yet. We're going to have to come back to it, because I know 3 to the first is 3, so y has to be bigger than 1. 3 to the second, 3 to the 2 is 9, so it's just too big. So it's somewhere between 1 and 2, but I don't know quite what it is. But here's the answer to the actual questions that's being asked. Can we rewrite these logarithmic expressions in exponential form using the little circle as the definition of the logarithm? We're able to figure out how we do that. Of course, we can go back the other direction as well. If we're asked to rewrite these in logarithmic form, we've just got to fill in the blanks, right? The log here has a base that's the same as the base here, which is 2. The number it's equal to is the inside of the logarithm, and then the exponent is the output, right? So 2 to the 5th equals x. So that's the logarithmic form for this equation. All right, equivalently, I can do this one. That's going to be log base b of 8 is 3, and I could rewrite this as log base e of 9 is equal to y. That's how we would rewrite these expressions in their logarithmic form. Now, let's use the definition of logarithm to evaluate these logarithms that we have right here. So we're trying to find what this is equal to, right? Remember that this means 10 raised to the other side is equal to what's inside. Now, can you answer that question? 10 raised to what power is 100? Well, I don't have to write it that way. I can write this mathematically. 10 raised to something equals 100. What goes in there? The answer is 2, right? So log base 10 of 100 is 2. So anytime you see a logarithm, that's all you're really asking. Log base 10 of 100 is what power do I have to raise the base to get to the inside? What power do I have to raise 3 to get 3? Right? First power. That's how I get it, because 3 to the first is 3, right? That's where that comes from. All right, now, what do I have to raise 36 to get 6? Now, it's not 2. That's backwards, right? I've got to take 36 to the something power and get 6. So how do I do that? Well, recognize 6 is the square root of 36, right? And how we do square roots as exponents? Well, that's 1/2. So the answer is 1/2, since 36 to the 1/2 is 6. So 2 there, 2. There are a couple of basic properties of logarithms that are fairly clear from the definition of the logarithm. For example, the first property I have here, log base b of b. B to what power gives b? Right, that's simply the first power, right? B to the first is equal to b. Okay? All right, what about the second property? B to what power will always give me 1? No matter what b is, I raise it to what power, that gives me 1. And that's the zero exponent property, right? Anything to the 0 power is 1. So clearly in these two examples, if I have log base 9 of 9, that's 1. If I have log base anything of 1, that's 0. So in this case, log base 8 of 1 is 0. Those are a couple of important properties that you'll need to know about logarithms. Another couple of properties that are important to know and are going to be particularly useful in solving equations comes from the property, or I guess the very definition of logarithms, as being the inverse of the exponential. Meaning that if I take an exponential, like b to the x, and then I take the same base and do log base b, those cancel each other out, and I'm left with x. And if you listen to the question that's being asked, it's obvious why that's x. All right, listen to this. If I say log base b of b to the x, that means b to what power is b to the power x. Right? The answer is in the question. The answer is x. Similarly, if I look at b raised to the log base b of x, I'm taking the exponential of a log with the same base, I'm also going to get x. The exponential and the log cancel each other out, because the logarithm base b of x, that means the power that I raise b to get x. Right? That's what this exponent right here means. The power that I raise b to get x. Then take b to that power. Well, that's the power that gives me x. So that's why I get x. So clearly here, log base 4 of 4 to the x is going to be x. They cancel each other out. And here, 6 to the log base 9, sorry, base 6 of 9 is going to give me 9. They cancel each other out. They cancel each other out. Let's take a look at graphing logarithmic functions. And just like we did with exponentials, we're going to do this using a value table. Now this can get a little bit tricky, so pay attention to the trick that I do here. Normally we pick values for x and plug them in. Now the reason why that can get messy is, say I pick the number 3. That immediately is a hard problem to get the answer to, right? If I say, what's log base 2 of 3? 2 to what power gives me 3? I don't know that, and in fact it's not immediately obvious how I am even going to use my calculator to figure that out, because my calculator knows 2 logs. It knows the natural log, which we haven't talked about yet, and it knows a common log. Neither one of those is log base 2. Alright, now to make life a little bit easier, what I suggest that we do is pick values for y and then find the x. That works out pretty easily. Okay, so say I pick 0. That is, I say 0 is equal to log base 2 of x. That means 2 to the 0 is equal to x, right? So what is x? X is 1. Anything to the 0 power is 1. If I pick 1, that's log base 2 of x is equal to 1, or 2 to the first is equal to x, so I get a 2. Similarly, if I pick 2 for y, I'm going to get 2 squared is equal to x, just by the spiral doohickey. So that gives me 4. Now what if I went down the negative direction? What if I tried -1 for y? That's -1 is equal to log base 2 of x. It's going to give me 2 to the -1, which is 1/2. Similarly, -2 is going to give me 1/4 according to the same pattern. Now let's look at what we can see whenever we graph this thing on the actual Cartesian coordinate system. So let's see, the first point that we know is 1, 0. So here we go. Right there is the point 1, 0. So our next point goes over 2 and up 1. The next point after that's going to be over 4 and up 2. So we plot right there. Okay, so now the next point is at 1/2 -1, so we end up right here, and the next point is at 1/4, really close to the y-axis. And you can see the shape of this curve appears to be something to this effect, which is similar to a kind of curve that we've seen before. Notice how down here at the bottom we end up getting closer and closer and closer to the y-axis the further down that we go. Okay? And as we go up off to the right, this thing seems to grow without bound. There is nothing on the left-hand side, right? And the reason is because we can't plug in negative numbers in for x. You can't plug in 0 for x. You can't plug in negative numbers for x, because you can't take the log of a negative number or of 0. So that's why this thing only appears on the right-hand side of our graph. So for example, if I tried to take log base 2 of a -1, I'm asking 2 to what power gives me a -1, and nothing I can stick in here would make that in fact negative. No, if I put 0 in there, that's 1. If I put a positive number, it'll be like 2 to the first, which is 2. So if I put in a negative number, it wouldn't give me a negative, it would give me 1/2 or 1/4, so forth. It's not possible. Okay, so it's important to remember that. I want to take a second here to compare for you the graphs of exponential functions and the graphs of logarithmic functions. I told you before, if you kind of turn your head on your side, you would see a connection to something that looked like an exponential function, right? Well, there's a better way of looking at that. You'll remember that the graph for, say, y is equal to 2 to the x looks something like this. Right, that's 2 to the x. And as we just saw, the graph of the logarithm base 2 of x looks something like this. That was log base 2 of x. Now what is that connects these two is the following. If you were to draw a 45-degree line, right, or a line of slope 1, where the rise is equal to the run, okay, these two functions are mirror images of each other. Okay? Now that is in fact a property that all inverse functions share. They're always going to be mirror images of each other. Similarly, if instead of taking 2 to the x, I did a base of 1/2. That is, I looked at y is equal to 1/2 to the x. You should remember that that looks something like this. It started out low, still crossed at a height of 1, but then it was decreasing from left to right. Okay, so if that's 1/2 to the x, what does log base 1/2 of x look like? Well, by that same principle, it's going to be a reflection about this diagonal, which means it's going to look something like this. It's going to be close here, okay, and then grow something like this. There is your log base 1/2 of x. It's basically taking the log base 2 of x and mirroring it about the x-axis. Okay? Here are a few characteristics to note about the logarithmic functions, log base b of x. The x-intercept will always be 1, and there is never a y-intercept. In both cases, whether it's log base 2 of x, log base 1/2 of x, if your base is bigger than 1 or less than 1 but still positive, your y-axis is always going to be a vertical asymptote. That term we've used once before, and here it just means that the curve will get closer and closer to that line but never actually cross it. Okay? Now if the base is bigger than 1, then the function is increasing as we go from left to right. Right? For example, log base 2 of x, as I move from left to right, it's going uphill. But if b is, of course, still positive, but less than 1, it's going to be decreasing as I go from left to right. Like we've seen fairly often in this course, a type of application that might be given for these new types of functions would just be a problem where a known formula is provided. It's interesting that there are some real-life physical examples of logarithmic functions that we're fairly familiar with. We just didn't know they were logarithms. One of those is the Richter scale. The Richter scale measures the magnitude of earthquakes, and one way to interpret what the Richter scale means is by this formula right here, that r is equal to log base 10 of I, where r is the Richter scale value and I is basically a measure of intensity. We're going to think of it in the following way, that it's the number of times greater than the smallest measurable activity. Okay, so if r, say, is 4, can we find I? In this formula, that would mean 4 is equal to the log base 10 of I. So 10 raised to the 4 is equal to I gives me that value. Just convert to exponential form to find the answer. I would then be 10,000 times more intense than the smallest measurable activity. Now it's interesting to me to note then that the reason why we don't see Richter scale values just blowing up way up off the top of the scale is that every 1 point value increase in the Richter scale value means a 10-fold increase in intensity, right? If R, say, was 5, then that would mean I was 10 to the 5th, according to the same thing that we got here. Now, that means 100,000. 1 point higher is 10 times more intense. Okay, so if you went from 5 to 6, that's another 10 times more intense. 10 times more than that would take me up to 7, and so forth. And so that's how this Richter scale works as a logarithmic type function. Another example of a logarithmic function is the decibel measurement. I alluded to this earlier, but there's a couple of logarithms that are more used than others, especially because your calculator knows these two types of logarithms. We have something called the common logarithm, and we're going to look at one called the natural logarithm. A common log is the logarithm with base 10. Okay, whenever we see log base x and there's no base, then it is understood, at least within this class, to be a 10. Okay, so log without a base is the common log. When you look on your calculator and you see an log button, that is log base 10. So in this example here, where we've got a formula, we've got a log with no base, we're going to assume that's a common log, meaning it's log base 10. The percentage of adult height attained by a boy who is x years old can be modeled by the following formula. F of x is equal to 29 plus 48.8 log of x plus 1, where x represents the boy's age, and f of x represents the percentage of his adult height. So, approximately, what percentage of adult height has a boy reached whenever he's 8 years old? To figure that out, just plug in x equals 8. So f of 8 would be 29 plus 48.8, the log of 9. Now, how do I get 9? Actually, I should go ahead and do this. 8 plus 1. So 29 plus 48.8 log of 9. Now, I'm going to go to my calculator for this. My calculator knows how to do the common log. I will do it first and then multiply. So log of 9 is 0.9542. This is equal to 29 plus 48.8 times 0.9542. So if I multiply that times 48.8, I get 46.567. That's plus 29, so add 29 to that. I have 75.6. And according to the model, that means that a boy has reached 75.6% of his adult height on average by the time he reaches age 8. Another often used logarithm is something called the natural logarithm. This tends to be used more by mathematicians, whereas the common log is used more in mathematics of finance, in, say, physics, etc. So the natural log is a log base e. We will write that as ln, short for, we want to start with L because that way logs all start with L, but n is short for natural, so the log that's natural or natural log. This is read as the natural log of x. Okay, so looking at this example here, before we do any practical applications of these, I just want to make sure that you're clear that you can see the relationship between the natural logarithm and that natural base, right? E being that number that we described in the last section, or 2 sections back, I should say, of 2.7182818, etc. Natural log simply means log base e of whatever is inside. So log base e of e to the 7x would look like this. And you'll remember that log base e of e to a power cancels out and you're left with 7x. So natural logs and e's to the power cancel each other out. Similarly, e to the natural log is going to cancel out because they're inverses of each other, and you'd be left with 4x squared. Natural log of e cancels, e to the natural log cancels. The United States has more people in prison, as well as more people in prison per capita, than any other Western industrialized nation. The function f of x equals 152.4 natural log of x plus 1107.7 models the number of inmates f of x in thousands x years after 1994. Use the function to find the number of inmates in 2006. So to find x, I'm going to say how many years have gone by since 1994 by taking 2006 minus 1994, which is 12 years. So I'm going to let that be x. So f of 12 would be 152.4 times the natural log of 12 plus 1107.7. Evaluate the natural log of 12. Again, I'm using my calculator. Just taking the natural log of 12 gives me 2.484907. Rounded. Multiply that times 152.4. I'm going to add to that 1107.7. So multiply by 152.4 and I get 378.7 plus 1107.7 gives me 1486.4 roughly. Now that's in thousands, right? So 1486,000. So 1,000 means basically that I'm going to have 1,486,000. So I move the decimal place 3 to the right. In other words, I have this many inmates. 1,000,000 is a million, by the way, in case you were unaware. Okay, and that's the end of section 9.3. We are now going to look at a few more properties that logarithm has, that the logarithm function has in section 9.4.